So, hello everyone. Welcome again to this new lecture. So, in the last lectures, we have been learning about the Sommerfeld model. It was the idea of describing things with a quantum picture. So, it was a transition from the classical picture to the quantum picture. Electrons are no longer treated as classical hard sphere-like particles, but they are quantum particles. So using Sommerfeld's ideas, we came to know about the density of states. We calculated the density of states. We calculated the occupancy, uh, which is basically the probability of occupancy, and which is the density of the occupied states. We came to know about that. So, and we also, at this point, we also know about the Fermi sphere, where up to that level in three-dimensional K space, up to that level, all the electrons are filled up, and beyond that, the electronic states are vacant. So, just recalling some of the previous things. So, yeah, recalling some bit of Sommerfeld's. Okay. All right. So, basically, if you consider 2D space where your Fermi sphere is like this, your Fermi sphere is like this. Okay. Within the sphere, all the electronic levels are states are filled. Now the electrons are filled up to this surface of the sphere. All right. Fine. And also they are in this space, scattered within the sphere. This was occupied states, occupied states, and these are your vacant states. All right. So now let me just clarify. This is a y. This is a x. So if you are not applying an electric field or a magnetic field or any kind of force, so the center of the Fermi sphere is this center of Fermi sphere. As we are dealing in the momentum space, so the center of the Fermi sphere will give you the zero momentum state. So the center of mass momentum, if you don't apply an electric or magnetic field or any kind of force, so in that case the center of mass of the Fermi sphere will be zero, center of mass momentum. All right. Now if you apply an electric field in the y direction, all right, so this is the y direction, this is your fine. So the corresponding force due to it will be given by minus E y cap. All right. So now the picture was like this. The picture was like this. So earlier you had like this. You had the Fermi sphere like this, and this was your old. So I'm extremely sorry, my pen malfunctioned. Let me just delete this part. Yeah. So, this these parts. Yeah. So this was your minus electronic charge y times y, and this was your volt p center of mass equals, which was originally 0 because you did not apply any magnetic or electric field or whatever. But now you have the, the electric field applied in the y direction. All right. So now the force is in the minus y direction. So what will happen is that the electrons, they will start to move because of this force. They'll feel the Lorentz force. Accordingly, the Fermi sphere will move along with it because the Fermi sphere defines the occupancy of the electrons in the energy levels. Their energy levels will change also because you have applied a force, and accordingly the momentum will change, and momentum is related to energy. All right. So now your new position will be here. Let's say this is your new Fermi sphere. This is your new Fermi sphere. All right. Fine. So now your new your new so this is your new PCM, which is not equal 0 because the center of mass has shifted. All right. So this was K vector is m v center of mass by over h cross. All right. So that defines the center of mass momentum in the K space. All right. So this was our picture of the Sommerfeld's model. We knew about the density of states. We knew about the Fermi sphere, Fermi wave vector, Fermi velocity, and all those kinds of things. Now, what we are interested in is to learn about the specific heat of the electron gas inside the metal. So now, what we are going to learn is specific heat of the electron gas inside the metal. Let me add, this is still a non-interacting gas. This is still a non-interacting gas. Let me just check whether it's recording. Yes, yes, absolutely. So now what we started with is the cubic box. The cubic box that we had, where Sommerfeld imposed the periodic boundary conditions. All right. So this is your L, L, and this is the L. And the electrons were moving about freely inside this box. All right, but they are non-interacting. Remind you, they are non-interacting. And Sommerfeld imposed the periodic boundary condition. What was its implication? Psi of x is equals to psi of x plus L. It did not go to 0 at the boundary of the container of the vessel it's in, but it has to be periodic. That was Sommerfeld's consideration. Similarly, psi y was psi y plus for a symmetric box. Every length scale is L, and psi z was psi z plus L. Fine. Up to this, we are good. All right. With the consideration that uh, the electrons are classical gases, the electron gas is a classical gas, with the consideration, with the consideration, the consideration that electrons are classical particles, meaning in the Trudeau's picture, there was no potential energy because there was no interaction. So only kinetic energy. So only kinetic energy from the equipartition theorem. This is Trudeau's picture. This is Trudeau's picture. We had equals 3 over 2 n kBt, where n is the number of electrons. And this defined the total energy also, because there's no potential energy. So now if you have to define the specific heat, which is your CV, that is dE total. I'm not writing total in the subscript, divided by dt, and that will give you 3 over 2 n kb, and which is again equal to 3 by 2 r. So this was the classical picture which we get from the Trudeau's form. All right, but things are not that simple, because what we already saw is that at high temperature, rather than being 3 by 2r, it's actually 3r. It's actually 3r. Fine. Now, as you went down with temperature, the specific heat behaved as T cubed. All right. So it went down slowly with temperature and attained the zero value. So this was due to the, so this was T cubed. This was T cubed, and this was the ionic contribution. Fair enough, because mono, the lattice vibrations. So you know that there are not only electrons in the solid, the ionic counterpart, which are heavy, immobile, uh, positive ion cores, they are there in the solid. So what happens is that if you supply a sort of an energy, then those ionic cores absorb the energy. All right, and they start to vibrate. Because of this vibrational energy, there's rise in the energy of the system. Because of the vibrational energy, there's rise in the total energy. So with the involvement of the ionic cores, you see an anomalous behavior compared to what you were expecting, that it should be constant 3 by 2r. Neither it is 3 by 2r, it's staying constant at higher temperatures, but it's 3r. Beyond that, as we go down with temperature, it's varying as T cube. It's not remaining constant. That's the most important part, and that is happening because of the ionic cores, because they're involved in the energy redistribution. All right. So as this total energy increase, so the ionic cores, will contribute to the contribute to the specific heat. So specific heat due to vibration of ions decreases as the heat. All right. So now what you expect that as you go down to very low temperatures nearing the absolute zero of temperature, as this goes down as T cube, it will go even less than what you expect for a linear behavior. So it will go down much more faster. So it will reach the zero absolute value. So this is the natural thinking process with the information that I have supplied to you till now. All right. But you see, in practice, this is not the case. As you go down to very low temperatures, so this I should yes. So messy. So this was your phononic contribution. All right. Yeah. But you see that as you go down to very low temperatures, it is not like that. It varies as CV varies as T. It varies linearly. So this is the important. So this is the important conclusion or important message of this lecture, which we are going to discuss more deeply. So I'm making the statement is that CV is proportional to T. Where from this is coming? This is coming because of the electronic contribution to the specific heat, and this happens only when you reach very low temperatures, which is below 4.2 Kelvin, which is the liquid helium temperature, or sub Kelvin of temperatures. All right. So this linear dependence of the specific heat was the evidence of the contribution to contribution to CV by electrons in the solid. All right. So this is this contribution. So this contribution only adds up at very low temperatures. All right. So and this happens happens only after the vibrations of ions inside the solid have almost ceased. All right. So as you go down to very low temperatures, the energy required for the vibration of the ionic cores will be almost negligible, and they'll stop vibrating, and therefore will not contribute to the energy increment, and hence will not contribute to the specific heat. Rather, the electrons will take over and they will contribute linearly to the specific heat. So let me remind you of the picture we have. So these are the ion cores. So these are the ion cores. All right. Now they are attached. They're attached with the spring-like structure to each other. All right. This is like this. This is spring-like structure that bonds them together. The salt. These are the heavy ion cores. So let me write this as positive, 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 positive. Now the electrons are also inside it. So electrons are inside them too. This is electrons in them. All right. So at higher temperatures, at higher temperatures, contribution of these electrons of these electrons to CV is dominated by contributions from atoms or ions in the solid. Fair enough. But as they go down to low temperatures, at low temperatures, thermal energy is not sufficient. Thermal energy is not sufficient to move these heavy ion cores. Understood? They don't, they almost cease to exist. Or sorry, this is to vibrate. So at low temperatures, thermal energy is not that much sufficient to move these heavy ion cores, and so the contributions from these ion cores, that becomes diminished, and the electron contribution to the specific heat dominates. All right. So because of this, the specific heat can be different color. So also check if it's recording. Yeah. So the specific heat can be written as d dt is equal to CV, that is ion vibration, plus CV that comes from the electron gas. All right. So at low temperatures, CV is neither 3 by 2R, comma, or 3R, or proportional to T cubed, but CV is proportional to T. And this basically comes, this basically comes from the Sommerfeld picture of electron gas in the metal. All right. So now, before proceeding further, as we want to know about what's the electronic contribution to the specific heat, let me just clear the picture of what specific heat really is. So specific heat is dq dt, means that if you change the temperature of the system, or sorry, it can be said in either way also. If you change the temperature of the system, what is the rate of change of energy, or rather, if you supply some heat into the system, what is the change in the temperature of the system. Let me just refresh. So if you supply, if you change the temperature of the system, what is the change in the temperature, change in the energy? Alternatively, it can also be said that if you give some supply some energy into the system or heat into the system, what's the change in temperature? So CV is basically the rate of change of the heat or the energy with temperature. So this can also be written as dEdt. Fine. So this is, if you change T, if you change E, how much, how much is the change in the energy of the system? Fine. So this is what it is. And now, to clear the picture even further, read about the energy levels that the electron resides in. All right. So these were the energy levels that the electrons reside in. Now, this will be filled up to certain level. Let's say it's filled up to this point. So the Fermi energy will be up to this level. This is U. All right. So this is the chemical potential. All right. So now, if you supply an energy kVT, that means you increase the temperature of the system. All right. Then these electrons, the uppermost electrons that is on the superficial level in the energy space, the topmost electrons will tend to move into the higher energy levels. This is because these energy levels are vacant. So this opportunity for the outermost electrons to reside into those energy levels and move out. So so let's just say you do this at temperature T equals 0, which is the simplest case, which is the Fermi energy. All right, picture is clear. So now think about that these electrons will not be able to move out because they are completely filled. The innermost shells or the energy levels are completely filled, and they do not get the the extreme innermost levels, not just in and around the Fermi energy, the lower energy levels, they don't have any vacant energy states to go into those electrons. All right, so they will not move out, but the outermost electrons that are near the Fermi energy will move out to higher energy levels. So dE, so the change in energy, if you supply, you increase the temperature of the system, you supply an kVT, the change in energy of the system will be dE. So only those electrons, E minus, which are near the Fermi energy, here participate in this excitation. Fine. So now, as electrons move out to higher energy states, the mean average energy will increase. So now you can understand that if you supply, if you increase the temperature of the system, the outermost electrons move out to higher and higher energy levels, followed by the next line levels, they will move out to the next energy levels. So in this way, the electrons will move out to higher energy levels, and as a result, the mean average energy of the system will increase. All right. So this is the principle of the specific heat. You supply, you let's say you increase the temperature of the system. What's the increase in the energy of the electrons? And this is beautifully explained by the Sommerfeld picture. All right. So now this is concerning the electrons. Till now, what we have learned about the 3/2R, those 3R, and the specifically proportional to T cube, that all comes from the lattice vibration. So 3R, comma CV proportional to T cubed, this all comes from the lattice vibration consideration. Now to look at the contribution of the electrons, the specific heat, you have to go down to even very low temperatures. So all right. So at low temperatures, CV, in earlier lectures, I said that CV of electron gas is proportional to T, and this is only 0.01 of 3/2R. So this is very small, but at lower temperatures, the phononic contribution or the lattice vibration will not contribute to the specific heat, rather the electrons will take over. Now we are into calculating. With this picture in mind, we are about to calculate the electronic contribution to the specific heat. So as I told, with the emphasis that this is all done at T equals 0, right? So up to a certain energy level, which is the Fermi energy, the electronic levels are filled. So if you supply a temperature, like right, if you increase the temperature, it's natural that you are not in the regime of T equals 0. So the change in energy, change in energy del E will be given by epsilon T minus epsilon T equals 0. Fair enough. So this is energy at finite temperature, and this is energy at. So this was our aim. We have to calculate the change in energy as you supply the temperature change. All right. So energy at T equals 0. Okay. So we have to make use of the different things that we learned in the Sommerfeld model. So our G of Ek times Fermi-Dirac Ek minus mu was the occupancy at of states, occupancy of states at Ek. Rather, it can also be written as the density of occupied states. So GEK was the density of states. Coupled with the Fermi-Dirac distribution, which gives the probability of occupancy, we'll get the density of occupied states. So density times the probability. So this implies that, so the number of occupied states, between energy Ek and Ek plus d of Ek will be given by g of Ek times Fermi-Dirac times the difference in energy, which is d of Ek. All right. So the number of occupied states in the energy interval d of Ek will be given by g of Ek times the Fermi-Dirac distribution. Let's say at a finite temperature T and times the dEk, which is the interval of the energy that you are going to consider. So each of these states, you are considering a spherical shell in the energy space. So consider the energy levels all have energy Ek. Each of the states have energy Ek. To consider that it's not variant over that energy level d of Ek. The total energy of the system, therefore, the total energy of the system, therefore, so let me first write between E and Ek and E plus d of Ek, between Ek and Ek plus d of Ek will therefore be given by Ek times the number of energy levels, Ft Ek minus mu times d of Ek. All right. So the total energy of the system at a finite temperature will be given then by total energy is then given by, this is only concerning the energy Ek, but you have other energy levels apart from Ek, that is spanning from 0 to infinity. So basically you have to integrate this term, and the integration limit will go from 0 to infinity because you have an infinite spectra of energy levels, but discrete, of course, discrete. This is G of Ek times Fd Ek minus mu times your d of Ek. All right. So now this can always be written as 0 to Ef. We split it into parts. This is Ek, this is G of Ek, this is Fd Ek minus mu, Ek minus mu, d of Ek plus Ef to infinity, Ek, G of Ek, Fd Ek minus mu times d of Ek. All right, we just split it into two integration intervals. On the other hand, the energy at 0 temperature will similarly be given by 0 to infinity Ek, G of Ek. Now the Fermi-Dirac distribution is Ek minus mu at T equals 0 times d of Ek. All right, so this is your Fermi energy. So again, splitting this into parts, this is Ef Ek, G of Ek, Fermi-Dirac Ek minus Ef, d of Ek plus Fermi energy to infinity, Ek, d of Ek, Fermi-Dirac Ek minus Ef times d of Ek. So you know that the Fermi-Dirac distribution Ek minus Ef is 1 for Ek lesser equals to Ef and 0 for Ek greater than Ef. Now, if you just put this into this above term, what you get is 0 to Ef Ek G of Ek times d of Ek, because in the interval of Ef to infinity, Fd is 0, and in the interval 0 to Ef, this is 1. So this is easy to calculate. All right. So now let's get back to what we wrote earlier as delta of E is equals to E of T minus E of. So we wrote this form where the difference in energy, is given by Et minus E0. So we split it into parts. The Et, we split it into two parts, and wrote the epsilon naught, which is the concerning the energy at T equals 0. So this is one form that we should number. So this is our equation 1. Alternatively, we also know another definition where this I should write it as n is 0 to infinity g of Ek Fermi-Dirac Ek minus mu times d of Ek, which is again equal to 0 to Ef. Sorry, again equal to 0 to infinity g of Ek Fd Ek minus Ef mu at t equals 0. All right. So now this 0 to infinity g of Ek Fd Ek minus Ef d of Ek, this can be split again into two parts. 0 to Ef g of Ek Fd Ek minus Ef d of Ek plus 0 to, sorry, this is Ef to infinity g of Ek Fd Ek minus Ef d of Ek. All right. So the first term will survive. So only this is 0 to Ef g of Ek, which is 1, F Ek minus Ef till Ef is 1. So d of Ek. All right. So of course this was per volume. This was I should write per volume. So n was 2 times k Fermi-Dirac epsilon k minus mu at t equals 0, which is 2, summation k Fd Ek minus Ef. So that was a summation form, and we wrote it in integral form. So n by v, remember it was divided by the volume. So n by v was 0 to infinity g of Ek, which we just wrote, Fd Ek minus mu at a finite temperature d of Ek is equals to 0 to Ef, 0 to Ef, 0 to Ef g of Ek times d of Ek. So this is what we get. Earlier we also saw that 0 to infinity for calculated at mu t not equals 0. So this term, this can be split also, right? G of Ek Fd Ek minus mu t d of Ek plus Ef. So this is Ef times infinity. So again g of Ek Fd Ek minus mu down d of. So this may be boring, but just follow with me and we will arrive at the final result. And again, this is equal to 0 to Ef, g of Ek, e of Ek. This is at mu at equals 0. So now what we are going to do is multiply both sides of this equation with Ef, which is the Fermi energy. Multiply both sides with F. Multiply both sides with Ef. So this will look like 0 to Ef, Ef g of Ek Fermi Dirac, Ek minus mu t, d of Ek plus Ef to infinity, Ef g of Ek Fermi Dirac, Ek minus mu t, d of Ek is equals to 0 to Ef, Ef times g of Ek times d of Ek. All right. So now this just bring those terms from one side to the another. So this Ef to infinity, this implies Ef to infinity term, which is given Ef g of Ek Fd Ek minus mu t d of Ek will be given by 0 to Ef g of Ek d of Ek minus 0 to Ef e of f g of Ek d of. All right, so this is what we get. Fantastic. So now, all right, so this I made a mistake. So this should be, this should be plus and this should be minus. So we write this as, sorry. So let me just erase this part. So write freshly. I missed a term. Missed a certain term. So that is a very big mistake. So this is like 0 to Ef. This should go first, minus 0 to Ef. Ef g of Ek Fermi Dirac Ek minus mu t d of Ek. Let us number this equation with equation number 2. You notice we are trying to make this two equations on the same footing and manipulate the terms in equation 1 with the help of equation 2. So for this lecture, let us just stop here because it will be a lengthy calculation and we tend to lose patience. So let us just stop here and we will continue with the calculations in the next lecture.